Okay, so we're doing section 6, or chapter 6, section 5, and that's the graphs of the tangent, cotangent, cosecant, and secant. Okay, so we're going to look at tangent. Tangent is a series, I think of it as a series of cubic functions. So we remember tan is sine over cosine. So when we're graphing functions, we want to look at our important angles. So we definitely want to graph pi over 3, pi over 6, pi over 4, and 0. Once we graph those, we can get those key points. And in fact, when I ask you to graph, usually those key points are going to be required on the graph of a trig function. So when we pull out these points, and so go ahead and write this on your graph paper, we are doing increments of pi over 6, because you remember, tan has an asymptote at pi over 2, and then repeats itself. Okay, we just graphed this middle one here, and if you look, it looks similar to a cubic function. So I relate tan in my brain, similar to a cubic function. Our asymptotes are on the pi over 2's. So we throw down an asymptote at pi over 2, 3 pi over 2, 5 pi over 2. And we can go ahead, we cross at pi, 2 pi, negative 2 pi. And remember, we can input numbers from negative infinity to positive infinity. Any number is okay to input. We just can't input odd multiples of pi over 2. It sounds like when you tell, telling people, I'm allergic to water. You go, what? Wait, say that again? Oh, odd multiples of pi over 2. And then the range is all numbers between negative infinity to infinity. All right, so that's the tan. The domain is all real numbers except odd multiples of pi over 2. The range is all real numbers. It's an odd function like a cubic, as the symmetry of the graph with respect to the origin indicates. The tangent function is periodic. It's got a period of pi. So it takes from negative pi over 2 to pi over 2. That whole distance on the x-axis is pi. So it gets through one period in a span of pi. The x-intercepts are at negative 2 pi, negative pi, 0, pi, 2 pi, and 3 pi. So it's consecutive integer multiples of pi. And the vertical asymptotes are negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2. That's the odd integers, multiples of pi over 2. All right, so now we're going to translate it. So graph functions of the form y equals a tan omega x plus b, and y equals a cotangent omega x plus b. So if we're going to take our tangent function, what we know about transformations is 2 tangent x minus 1 is going to take our tangent function, move it down 1. So where we were crossing the x-axis at 0 is going to all be moved down 1. And then we are going to have a vertical stretch of 2. So here's our original tan function. We already have this written down, and I want you guys to graph y equals 2 tan x minus 1 on a separate piece of paper, or on a different graph than the one you had before. So when we do a vertical stretch of 2, instead of being here at pi over 4, 1, at pi over 4 we're going to be at 2, and at negative pi over 4 we're going to be at negative 2, like so. So start with your middle one. We're still going to go through, let's get our move down 1. So instead of being here at 0, 0, we're going to be here at 0, negative 1. And then we're going to go over pi over 4 up 2. Draw that. See how it's not as fat in the middle? It's nice and skinny in the middle. Same, the asymptotes still. They didn't draw it on here. The asymptotes are still the same. They did draw it on here. So doing a vertical stretch and a move up or down doesn't change the asymptote. So go ahead and on your paper, sketch the graph of y equals 2 tan x minus 1. All right. So now let's see what happens when we mess with inside the tan function. This is my least favorite type of translation because it so stretching by a factor of 3, totally cool with. All it does is instead of at pi over 4 being at 1, it goes pi over 4 on your x 3, so it makes it skinnier. I am totally okay with that. What I loathe is the horizontal compression by a factor of 1/2. So you look, so whatever this value is here next to the x, so that's 2, I take my asymptotes and I multiply that by 1 over that number. So before I had pi over 2, I'm going to multiply that by 1 over 2. Take this, put it over 1, and multiply it by your asymptotes. So now instead of being at 1/2, it is at 1/4. It wants to say it gets through your cycle twice as fast. So instead of cycling through having a period of pi, it's going to cycle through in a period of pi over 2. So this half is pi over 4, this half is pi over 4, so now my cycle happens twice as fast. So now instead of having pi over 2 and 3 pi over 2, we're going to have pi over 4, because I've multiplied it by 1/2, and 3 pi over 4. Twice as fast. So go ahead and graph this third one on your paper. Please make a note of how, because it's not anywhere here, of how we multiply our x values by 1 over the compression. 1 over, I guess they call this omega. All right, so cotangent, y equals cotangent. So our asymptotes are at 0, pi, 2 pi, negative pi, negative 2 pi. So it's consecutive integer multiples of pi. So throw down cotangent. The important points, so we cross at pi over 2. So our intercepts are at pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2, negative 5 pi over 2. The important points are pi over 4, 1, and 3 pi over 4, negative 1. So those are kind of the marking points that it keeps us square. We can input all x values as long as we don't have integer multiples of pi, and our output is all values between negative infinity and positive infinity. So that represents our domain and range. Okay, but look at cosecant. I love cosecant because cosecant is kind of like little parabolas. So, and then they alternate, one up, one down, one up, one down. They throw down the, can you guys identify, is this sine or cosine? This black line here. Who is cosecant studied is sine, yay. If they're like, they don't go together, I always think cosine, cosecant, they should go together. But it's like that terrible romance story where the people that you think should go together never are together. So sine and cosecant are together. So they threw down the sine function because cosecant is 1 over the sine. So it's each of these coordinates are flipped. So when we have wherever sine is equal to 1, cosecant will also be equal to 1. So we have these little parabola looking shapes at pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, negative 3 pi over 2. And they alternate. So here it's positive, the next period it's negative, the next period it's positive, the next period it's negative, the next period it's positive. So go ahead and take a moment and write those down. Our asymptotes fall at pi, 2 pi, negative pi, 0, and negative pi over 2. All the places where cosine is equal to 0, we're going to have a asymptote. And if you forget, you can just draw the sine function real quick and go, okay, all those places where cosine or sine is equal to 0, I'm going to have an asymptote. Draw those in. Our range is not going to fall anywhere, so it's all y values except the values in between positive 1 and negative 1. If you look, cosecant never outputs a number between positive 1 and negative 1. FYI. Or they write it as absolute value of y is greater than or equal to 1. All right. So here's secant. So secant is buddies up with cosine. And so this black curve is the cosine function. Secant is similar to cosecant. He's just a series of parabolas that alternate up and down. Between negative pi over 2 and pi over 2, he is up. If you can remember that one part, then you can throw down the rest of the graph, because you'll know we're going to alternate down and then up and then down and up. So the x values, you can input any x values between negative infinity and infinity except odd multiples of pi over 2, because that's our asymptote. And that these happen when cosine is equal to 0. So because cosine is equal to 0 at pi over 2, we can't go 1 over 0, so it's going to throw an asymptote in your direction. And just like cosecant, we will not get any outputs between 1 and negative 1. So our range are all real numbers except for those between 1 and negative 1. All right, so now let's mess with these functions now that we have the general graph. So we're going to fuss with the vertical stretch, horizontal stretch, and vertical movement up and down. Ugh. Okay, when I have two, look at all these graphs. When I have 2 times the cosecant of x minus 1. So all I want you to do is graph the final one here. So we are going to vertically stretch our graph by a factor of 2. So instead of having an output at pi over 2, 1, we're going to have an output of pi over 2, 2. So important thing to note is that the vertical stretch changes our vertex of those parabola shapes. Because we're stretching vertically, it changes our coordinate from 1 to 2. So please highlight or make a note, whatever y'all need to do. And then minus 1 means instead of being up here at 2, we're going to move it back down to 1. But then this guy at negative 2, we're going to move him down, boop, to negative 3. So we're stretching out that distance between our vertices. Instead of being 1 on the top and -1 on the bottom, it's going to be -2 and 2. And then we're going to move that whole thing down 1. So that means +1 and -3. Okay, so conclude for today. To take the cosecant, stretch it by a factor of 2, which changes our output to pi/2, 2, and -pi/2, -2, and then move all those down 1.